this lesson, we will take a closer look at the 7 life cycle design strategies developed by Politecnico di Milano. These strategies provide practical and concrete guidelines to help designers reduce the environmental impact of their products at different stages of the life cycle in relation to the functional unit. Each of these strategies is divided into several sub-strategies, which we will analyze in detail. The first strategy consists in minimizing material consumption at all stages of the product's life cycle. To achieve this, we can use several sub-strategies. First of all, we can minimize the material content of the product as Kohn did in the 1990s, when they created the first compact elevator without a machine room, which revolutionized the entire sector. Material consumption can then be reduced during the production phase by designing to minimize scraps and discards, and during the distribution phase by designing to minimize packaging. Finally, if the product consumes material during use, we can choose more efficient material consumption systems or adopt systems with flexible material consumption, where the amount of material used can be adjusted manually or automatically, as in sensor-activated faucets. The second strategy consists in minimizing energy consumption. Here too, the goal is to reduce energy use in all phases of the life cycle, but especially during the use phase and distribution phase, where the designer has greater control. It is important to emphasize that by energy, we mean not only the energy consumed during use, but also the consumption of energy resources during transportation, such as fuels. Here as well, we can choose the most efficient systems for energy resource consumption during use or adopt systems with flexible energy resource consumption. Finally, a last sub-strategy is to minimize energy consumption for transportation and storage. For example, by making products easy to stack, assemble at the place of use, or by creating concentrated products such as detergents and cleaning agents in soluble tablet form. In all these cases, in fact, the product volume is reduced, so more units can be transported in the same vehicle, thereby lowering the environmental impact during distribution. The third strategy is to minimize the toxicity and harmfulness of resources, that is, to design in order to reduce toxic or harmful emissions at all stages of the life cycle. To do this, we can first of all choose materials with zero or minimal toxicity, that is, prefer materials, additives, finishes, and production processes that are non-toxic or have minimal toxicity for human health or the environment. For example, some furniture manufacturers specialize in designing hypoallergenic and non-toxic furniture made with certified organic materials, non-toxic plant-based finishes, and without flame retardants. Another sub-strategy is to choose energy resources with zero or minimal toxicity. The fourth strategy consists in optimizing the renewability and biocompatibility of resources, that is, designing to increase the use of renewable and biocompatible materials and energy resources, resources that, once returned to the environment, do not compromise the quality of resources available in the ecosystem. In both cases, the goal is therefore to conserve resources for future generations. A first sub-strategy consists in choosing renewable and biocompatible materials, such as wood with certifications that guarantee its renewability, like FSC or compostable biopolymers. Among these materials, we can also include recycled materials, because they do not require the extraction of new raw materials, as well as materials derived from production waste. A good example are these outdoor pavements made from seashells and dredged sediments, experimentally produced by the Polytechnic University of Bari. If, on the other hand, the product consumes energy, we can choose renewable and biocompatible energy sources, such as the classic photovoltaic panels. Another fundamental strategy is to optimize the lifespan of products, meaning to design, given the same functional unit, to extend the useful life of the product, but also to intensify its use or to increase its reliability, that is, to reduce the likelihood of failures throughout its expected lifespan. There are several sub-strategies to extend the useful life of a product. We can design to lengthen the lifespan of components or design to facilitate the upgradability and adaptability of the product, both at the software and hardware level. A very interesting example is Fairphone, a mobile phone designed to tackle technological obsolescence thanks to a design that is easy to disassemble and upgrade. In fact, the user can independently replace various components, such as the screen or the camera, according to technological advancements or their personal needs. Other sub-strategies to extend the useful life of the product include facilitating maintenance, repair, reuse, and remanufacturing. The last two sub-strategies for optimizing product lifespan are intensifying use and designing for reliability. Another essential strategy is to extend the life of materials, meaning that the materials a product is made of, whether pre-consumer or post-consumer, do not end up in a landfill at the end of their life, but are instead recovered through recycling, composting, or energy recovery. Let's now look at the various sub-strategies, starting with adopting a cascade approach where the material is recycled and used to make components with progressively lower aesthetic or performance requirements. In fact, materials, especially polymers, tend to lose some of their properties during recycling, and so, after recycling, they often cannot be used to make the original product. For example, in the 1990s, Fiat recycled the bumpers from its decommissioned cars into internal air conditioning ducts, which were then further recycled into floor mats. And these, in turn, were finally used for energy recovery at the last stage of the cascade. Other sub-strategies to extend the life of materials include choosing materials with efficient recycling technologies, meaning those that best retain their performance characteristics after the recycling process, minimizing the number of incompatible materials, that is, materials that cannot be recycled together, such as plastics with different melting points. And finally, facilitating collection and transport after use, identifying materials, making it easier to clean the material, and facilitating composting or combustion for energy recovery. We conclude with the final strategy, facilitating disassembly, that is, making it easier and more cost-effective to separate either the parts of the product or its materials. Making it easier to separate the parts of a product simplifies operations such as upgrading, maintenance, repair, and so on, thus supporting the strategy of optimizing the product's lifespan. If, on the other hand, we facilitate the separation of a product's materials, we make it easier to recycle them, recover energy from them, or, if necessary, isolate them in the case of toxic or harmful materials. In this case, therefore, we support the strategy of extending the lifespan of materials. There is also another method of separation that supports the extension of material lifespan, the so-called crushing separation. In this case, the product is crushed and the various materials are separated using different technologies and then recovered for possible recycling or incineration. To facilitate disassembly, the main sub-strategies are reducing and facilitating the operations for disassembly and separation, using reversible joining systems or permanent joining systems that can be easily opened, and finally, we can co-design special technologies and features for crushing separation or use materials or inserts that can be easily separated once crushed. It is important to consider that, depending on the context, some strategies may prove more effective than others in reducing environmental impact, and in certain cases, they may even come into conflict with each other. Therefore, while it is important to pursue all strategies, it is essential to carry out an environmental impact assessment of the product in order to prioritize the strategies so as to maximize the reduction of environmental impact.